single bus bar input from the center of the rack. Then we're going to have Samir come up and do a presentation on the Facebook V2 PowerShelf. So this is the PowerShelf that's up here. So he's going to be focusing mainly on the AC-DC conversion portion of the PowerShelf. Then we'll have Zoe come up and go through the VDU, because the PowerShelf consists of both the AC-DC conversion as well as the integrated VDU functions. Chassis. We'll take a quick break, and then we can go through in glorious detail all the changes that were being proposed essentially to this group for the updates to the standard book 1.1. So this is Facebook OpenRack V2. So again, I'm just going to kind of go through the changes between V1 and V2. So the V2 rack is compliant to the current OpenRack standard 1.1. So it should also be compliant to 1.2, depending upon what the results of later on this afternoon are. But right now, everything that's proposed would still allow this rack to be compliant with 1.2 standard as well. Any IT gear that was developed for OpenRack V1 is still perfectly compatible with the V2. So there's no need to go and redo a lot of the IT gear associated with that. The maximum mass for the IT gear was increased from 950 to 1450 kilograms. We also increased the height so that we're at 87 inches for the rack frame from the floor compared to the 82.5 that we had on the original V1. So one of the things you'll notice is that on the OpenRack V1, we had 3 bus bars that were populated across the back. So OpenRack V2 can support up to 3 bus bars, but Facebook is choosing to only populate one of the bus bars, so just that central bus bar is what we populate. You'll also notice that the PDUs, which on V1 are located in the vertical posts on the entire height of the rack, now been shrunk down so that they're just 2 smaller boxes that fit up underneath the canopy inside the rack. So on OpenRack V1, there's 3 different power zones, 1 for each phase. For OpenRack V2, we changed so there's now 2 power zones, 1 on the bottom, 1 on the top. With the PowerShelf is now located centrally within each zone, as opposed to V1, which had it located at the extreme bottom of each zone. So the fact that it's in the middle helps quite a bit with the efficiency, as opposed to having to push it along the entire length of the bus bar from the top of the. If we take the rack away and just show kind of the power subsystem, it's kind of what you would see. So there's the ACPU that's powering the data center, distributes it to each of the power shelves. One each like I was saying before. So the total bus bar runs along the entire length of each zone and allows the IT gear to plug in, line mate into the bus bar in the back. So from there, just the power shelves also will generate DC as well. So the DC runs up with the DCPU, and from there it gets split off to run any gear that needs 48 volt. So in this case, we normally use that space for PID switches. But it really can be used for the So the power shelf has 6.6 kilowatts, 12 volts worth delivers. So there's 3 PSUs on the top, providing 2+1 redundancy. Top each EDU is displayed to the PSU that's above it. So each one is kind of a self-contained column, if you will. And there's a picture kind of the back side where you can see the different interconnects, as well as the interconnect between the power shelf and the central bus bar for each power. So again, that's just a very, very brief overview. Now we're going to start going into a little bit more detail. We're going to choose our come up and present on Cubby. Yeah. Turn it on. Good enough.
Okay, so Cubby is a general chassis that fits into the overnight splits. Each shelf into 3 slots. This shows different powers on this gives. So this is the left connected to the block. So what Cubby does is it takes bus bar power input and then splits it into the 3 slots and deliver what power to those slots. This is the so this is one nice capacity like Cubby. Another this is the cost. So we figured out what the maximum volume of each node will be, and this is the channels and load. But it fits before I showed that. So each individual IC chassis has a max range of amps. Before it goes back.
Yep.
Somebody has to ask you questions here. You sit through it, and be done in 20 minutes. Or maybe that's the goal. Do you have somebody here? No?
Power shelf. So here's one of our engineers on Facebook. Mine goes through, like I said, the power portion.
My name is Samir Pella. I work on the
Your mic is on. And you find any clicker.
so stop me at any time if you have any questions. Shouldn't be a long presentation, but let's get started. So I'll be talking about the differences between V2 and V1. I know some of you might not know what the V1 power shelf was, the one over rack. So I'll go through that. One of the main improvements that we made in V1 and V2 is we eliminated phase balancing. You'll see, I'll talk into more about that. V2 is also cost reduction, it's cheaper. V2 rack, as Steve mentioned, is slightly larger, it's 87 inches. The PDU now is more serviceable. Service it from the inside without V1, you had to move the rack to service the PDU. No one used windows or anything in the V2 shelf. And then the main stuff is, instead of having 7 power supplies in V1, we only have 3 power supplies now. And we've integrated the DC battery backup inside the V2 shelf. So on your left is what V1 power shelf open rack was with the 3 power shelves. And on the right is now the new V2. So you can see we had 3 power shelves, 1 for each phase. Now we have 2. 1 is the 2 phases. So in our data center, we would have this blue battery cabinet, which is 85 kilowatt battery cabinet that would supply battery backup. This racks here. V2, the lithium-ion batteries, that's all we'll discuss. They're integrated inside of the V2 shelf. No longer need the battery cabinet. So this is a quick running image of the V1 power shelf. There's 7 power supplies plus 1 redundant. Each power shelf is single phase. Here's some quick images for your understanding. You have the power shelf. It has 3 outputs, 12.5 volts, 3 bus bars. Everything gets connected to the IT30 connected to the clip. That's the bus bar. So this, we mentioned before, this is a V2 power shelf. So now we have 3 power supplies on the top and 3 lithium-ion battery packs on the bottom. The lithium-ion battery packs supply power, AC is out to the power supply. And here's a back image of the shelf where we only have 1 output bus bar right now. Instead of having 3, we have 1 center bus bar. Now we're, of course, AC input for it. Yes, that is how we do management for it. Output for both DC. Since we don't have the blue battery cabinet anymore, that used to power our switches to low voltage. We're producing our own 54 volts from the power supplies, and we're going to send that up to the station. So in the V1, you see that we had these fusion lug cables that would connect the shelves to go shorter to 3 bus bars. V2 now we just directly connect copper bus bars, raised with rat bus bar. That's another front image of what the shelf looks like. How to connect the back again. Here's the back connection. We have 4 bolts that connect to the negative side and 4 to the positive side. The rack is connected in the middle of the zone. That's just for copper losses. So we'll have about 265 amps going up this way and another 265 amps. So like I said, 6.6 kilowatts, around 530 amps at 12.5 volts. So this is a block diagram of the actual power supply, which is all in here. So I'll quickly walk through it. The input voltage to the power supply is single phase, around 180 to 290 volts AC. Goes to the EMI filter, there's inrush circuit limiter, bridge rectification, and then goes to EFC. Steps up the input voltage, steps up the voltage around 440 volts for our bulk capacitor. We also, the difference between this power supply is about 3 power supplies in 1. So we have our main LLC, or this one's the LLC circuit that does the DC-DC conversion at 3.3 kilowatts, and that produces a 12 volt output. But we also have a step-up converter that takes the lithium-ion battery voltage around 48 volts, steps it up, powers up the bulk voltage to 440. We also take the bulk voltage and we can step down the voltage to charge the battery back. So And we have a third converter that takes the bulk voltage and produces 54 volts DC, and that's the one that you use for the switch. So as you can see, there's about 3 extra converters in here in V1 plus. Some a little bit more technical specs about the D2 power supply. The input voltage range is about 200 300 volts AC. The DC input voltage range is 24.5 volts DC. Then we have 12.6 volt output, 3.3 kilowatts. Power temperature -5 plus 45 degrees centigrade, and the rough dimensions are around 5 millimeters by 105 millimeters by 500. So, the battery charger circuit that's inside the power supply is 270 watts. Takes the input from the bulk voltage and steps it down to precise 52.5 volts DC plus minus 0.2% output. The maximum charging current for the battery is 5 amps. We also have the backup converter, which is around 3.6 kilowatts. It takes the DC input voltage from the battery, which is 2.533 volts DC, and it steps it up to the 440 volt voltage. The efficiency during backup is around greater than 19.5%. We also have the auxiliary converter that I mentioned before that produces 4 volts for switches, the 300 watt converter, and the input voltage. Here's some data. Just we have a less than 5% sharing accuracy with the 2 power supplies. There's some data to show you that we actually do share very, very close to each other. The power supply efficiency is a titanium standard efficiency. So we have at 277 volts AC, and power supply meets it. So 10% of the loading we're 90% efficient, and 20% of the loading we're 94, and 50% we're reaching 96% efficiency, and 100% greater than 90%. Our power factor is greater than 0.95, when our load is greater than 10% loading, and our THD is always less than 10% whenever we're greater than 10% loading. So we have some logic that communicates between the VSU and the VDU. The VDU sends these 8 signals to the power supply, and these power supply takes in these signals to the answer code. So, I want to be charged, don't charge, do a state of request, so further the presentation, sleep signal, and reply, and search. And then there's a whole battery test logic also built in the power supply. So whenever the battery has to be tested for state of health, the PSU will run a series of tests that perform battery tests. Communication shelf is there's 40 wires, 45 coming out of the shelf. There's a CAN bus between the PSUs, the 2 PSUs, and then there is the SM bus between PSUs. So mechanical dimensions of the shelf is around 534.5 millimeters width by 139 height. That's the shelf. That's the power shelf. On the back of each power supply connector, we have one main connector that brings in the AC input voltage. It also brings out the 54 volts DC voltage for the switches, and then it also has input voltage battery that comes with and the battery inside of the shelf. There's input for the battery, negative, positive, and then some pretty connection as well. So inside the shelf, the main connectors we're using is a Tyco ground clip series 2 connector. These are the 300 M connectors that the power supply will open 5 volts out of. Base input voltage for the back of the shelf is a positronic 5-pin connector, which is here. That brings all 3 bases in. We have Molex Sabre connector for the 54 volt output. We have a 6-pin Molex 15 connector that's used for quickly talk about the PDUs. So as Steve mentioned, the PDUs have changed as well. This is an example of the DCP. So each one of these inputs will connect to the shelf, long jump, 1, further here than connecting here as an open port. The ACPDU, so we've built in surge protection inside of the PDU right here, and we have various types from 120, 208, 3400, 740. And Facebook data center, we run currently we run the 740, and they're going to get 3400. Yeah, so servicing the PDUs, you don't need to move the rack. All you need to have access to the back of the rack off of it. From inside of the top. I'll just try to find a picture. See if I can explain that better. So this is what the PDUs look like. This, I can find. Yeah. Yeah, we have these. You see that the ACPU sits here, the ACPU here. On both sides, there's a stable trough that goes down. So the PDU cord will come inside here and plug into your base. So if you want to remove this, there's just two tabs for it come out to the back. Yeah, because the cables and everything are hidden inside of this trough area. So even if it's here, you won't. Able to show the trough. And then over here, the switches normally end before. I have a natural sample of the shelf if you want to see it. So each power supply has the 12 volts connection, the 12 volt output coming from here, and then the AC, DC output and all of the connectors right here. So this is the back of the power supply. The back of these two bus bar blades then connected to the shelf bus bar system that's here, and so it takes the three power supplies and aggregates it into one output. And this one connects now into the bus bar rack. Any other questions?
Actually, I think it's a pretty innovative and efficient design, right? So you guys have gone from 3 bus bars down to 1. You eliminated a battery rack inside the data hall. And you're able to go from 3 power zones to 2 while maintaining the same kW rating.
Yeah, so the rack is still 2 shelves, 6.6 kilowatts each. So you can call it 30 kilowatts total per rack.
What's the expected duration for at full load of the battery life bringing out?
So for the base load power supply, we have a setting or a firmware setting that limits 90 seconds, even though the capacity of the battery might be longer. So we'll get into that. But we always limit to 90 seconds. Our generators turn on within about 10 seconds and then switch over. So we only need about 20 to 30 seconds maximum. You guess the server, the compute server, and the storage, they all work on one power. Right now, we're limited by our cap boxes in our data center, breaker box. Since we're using the 27740, we only get about 13 kilowatts of power per rack for the breaker. It's about 20 and 30. That's 2 percentage per line. We have 27740, that's 6 amps maximum per line. So right now, that's our limitation. And then also, each data center row, the busway row, has a limited power on it as well. 22-inch power in the rack just ends up with the one bus bar system will have more losses now. So if we do increase the power of the rack, we'll probably have to go back to a 2-bus bar system. From calculations right now, since the power supply is about 96% efficiency, through the whole distribution path, it's calculated we're losing about 1.3%.
Let's say on the IT equipment side, our models haven't shown us they're going really high on power density for rack. Part of that is we deploy people when it's an incremental cost of spreading out, and fueling efficiency. We built, yeah, it's a bit tall. Right now, we're actually not building the height. I think we overbuilt the height a bit in where we are right now. And we're currently keeping a little bit of headroom. It's one of those things where it's really cheap to overbuild space. It's really expensive to run out of space. So I'd rather put a few more panels in track.
Yeah, so here we have like 8 U space up here, and 8 OU here, so we have 16 OU right here per zone.
In the, what drove you guys from 3 zones to 2? Was it just that you could achieve the KW numbers in 2 power shelves alone?
So yeah, the KW is the same as 2-1. So we have the 4.2 kilowatt shells. One other thing that's helped us with this 2 zones is phase balancing. Before we had to put 10 servers on the top zone and then plus put 10, 10, 10 in the third.
Yeah.
Now we can just put 5 kW on top and probably like 1 kW on the bottom, and we want that to be phase balancing. That, and I guess also the cost for eliminating a lot of bus bars.
In the positioning of the power shells central to the bus, that's just to minimize the distance that you're trying to carry the current
Yeah,
across.
exactly. Yeah. So it's just all for copper losses placing. But as I said, we have 265 amps going top, and the 265 going bottom.
Can you describe the 54 DC connection? I didn't pick up on how you connect them for.
Alright, so at the back of each shelf, so each PSU has, as I mentioned, a 300 watt auxiliary converter. So each PSU is capable of 300 watts of 4 volts. So all of those get parallel together, and there's an open connector in the back of the shelf, which was that more like saver if we can connect it. Now from there, these takes in the input from this shelf and the input from the top shelf into this. And then these do there's 4 ports in front, and they will have that.
That's what it was. Okay.
So the DC connector on back here.
Do you intend to deploy another compute rack where the battery racks work? Or is the density of the data hall prevent that? So you eliminated the battery rack.
Yes, we eliminated the
So you guys plan to deploy where the battery rack positions were?
Yeah. So in our data centers, we have 24 cab positions,
Okay.
plus 4 for the battery cabinet, so total 20 positions. So now we can use those 4 extra positions that we gained by removing the blue battery cabinet to put in racks.
We do have a slight problem with our data center team side with a structural post there. So there are some cases we might put a blank container with the battery cabinet on us.
Battery cabinet. I don't want to. Here. Plus the roads. The dynamic, all the positions are filled and from power.
So and I think we have we budget on 150 kilowatts per row. There's 28 cab positions. For now, each rack is 10 kilowatts each, then we come 50. But that's what we.
Yeah. And so what was driving you to the taller rack? Just capability?
In V1, we had something here that sat on top of the rack. Now we just put everything inside. So that extra space just allows us, if we had any other products or anything else we want, we can just hide it inside of the rack.
That 87 inches also happens to line up with the body of the person. And, a lot of standard elevations for data center, everything comes there and that, that helps with autonomy.
Yeah. So what is the total OU height of the rack, including shelf? Are those 2.5 OU shelves?
So the shelves are 3 OU. So you have three, but there's 3 OU on top for the switches. Then you have 8 OU for the first half of this also, plus 3 OU for the shelf, and another 8 OU for the second half of the first one on this next 4 years. So another 8, 3, another, that's this fourth one.
So there's total
41 OU.
six. So normally they come with ready. So when they arrive at they get ready for the phone on the truck, holding with them. Not integrated. Only
Broadcast is from what you're saying.
right.
Mute your video.
Integrated.
How do you mute the
All,
Okay.
truck.
Okay.
Thank you.
We do have to move around, sometimes grabbed by air. So the standard, when you go to this, the standard is very, very basic, so it controls almost process against the rack. So it allows you to build your, so, this is just Facebook implementation. So, there's nothing standard that makes it high. So it's Facebook's quite. The 87 like Samir mentioned, civil is called for the add-on one. But basically, sure. 87 also happens to line up with more added. So this thing will hack it out. So now we get that. Matt mentioned we rather have slots inside the rack. Out. So I think Facebook loves. It is. 87 already jumped. Doing servicing. Talking around. Yeah. Yes. Good. On their crash card, they got right on it. Get caught.
We use Fidelity as well. Actually, no roll right. When you mentioned that, 50-51 did, we stopped ours at, we were like 10, 20, we're at 48 ours and 44 OU. We'd considered going taller, but we ran into tree on the truck. And be able to fit the rack on a pallet instead of sit on trucks. What's that? Are you doing aircraft? We're not doing aircraft, we're doing on trucks. That's phase one. So
Yeah, that's a good point. I know other people that have gone higher than 87 inches that can't get inside of a standard sea container. You have to get one extra tall. Well, yeah. You put 4 racks in the container, ship it that way, sure.
I just want to piggyback on Kurt. I will. There's some kind from that with our church good that is our why 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 not?
Sure.
Yeah, so right now our data center, the infrastructure is not built for the high voltage DC. One of my 2 points I would be that right now we're at 96% efficiency of the AC conversion. With the high voltage DC, it might be at 98%. But there's also a front part where you have to take the AC voltage and step it up to high voltage DC. So that's probably about 2 or 3% loss there. So right now, I think we're almost equal to the high voltage efficiency-wise. So we don't gain anything from efficiency by switching to high voltage.
Right.
Yeah.
Why or at you at some point for I thought that one they think was good and very from so you're saying from that one you're right. That was the last one.
Yep.
We're not very so that's the I was just ready to I'm looking forward to it. So that next time. But yeah, absolutely.
It's for our customers, like the Facebook data center group. So when their electrical guys tell us that, hey, we're going to pursue high voltage, we'll have to rethink of a new output way of power inside of that.
That is the part of the east out the right for us, we're talking one house or all the time, but we have the doctor or that this whole concept back in the 90s, like for the third when I was east of concept area, like right, that or
Well, I think the thing with the variable data center is it eliminates the need of the UPS within the data center. I think your integral battery backup gets you that same spot. So I think that both solutions get you to a solution where you eliminate loss of the UPS and possible maintenance.
Yeah, that's right.
Yeah, so we have a directive of 48277 coming in to the transformer straight into the building, and from there it goes straight to the half box to the PU. goes right to the power supply. So we eliminate a lot of that double conversion stuff that normally is.
So does your utility guys, they deliver 480 into the building, but their feed to your site may be
So the feed to the
30,
site,
34 kV, but they step down to 480 to the building.
no, the feed to the site is about 110 kV, and then we step it down to 12.5 kV, and then from there inside, inside the data center, it gets to the transformer, so it takes the 12.5 kV, steps it down 15%, down to 40. There, just gets distributed to that data center.
One question. So inside your facility line, you step down from 12.5 kV to 480, right? Why don't you get down to a little bit? No, let's say 440. In that case, you don't need to get 77 volt, right? Just take that amount, let's say 264 or something. So all the red and power play, you take that amount, get high.
Yeah, and then, well, the other thing is higher the input voltage to the power supply, the higher the efficiency. So the efficiency of the power supply is slightly higher at 277 volts input than 230 volts input.
Yeah, the cost is also much higher. Because all the components, you've got those. Cannot use most of like all the stuff on it.
I guess the other thing is the North American standard, the 40 standard, whereas the European standard is the 400, 230.
In the motors and mechanical plants, all the other elements of the data center in the US, it's like buying 480 volt gear, you know, it's relatively commoditized. We're trying to do water, gas, but, you know, it's more custom.
Due to that, you have fine price for you. Can you just
Oh, the center. Yeah, so that one is used for mechanical stuff. So right here, this one over here, it's just a mechanical, basically one.
Yeah, there's a big bar that we're on as well as both sides of the opening. So, yeah, that's it. So, like a traditional EIA rack, where you've got face plates that run all the way down, and we screw those face plates to either side, you get a little bit of rigidity, and get that into the rack. We're transporting fully integrated racks. What Meraki doesn't have, right? It's just open frame, right? The way our gear kind of slides into place, it doesn't have the screws and stuff that you have in the Christian guy here. So you don't have that additional mechanical support that you would normally get from kind of for free with the gear installed. So the bar just helps with during transport with the rack going. If you didn't ship it with the gear integrated, that's the way our model set up.
the bar space?
Yep, yeah, it's welded in. Yep, so it's not necessarily necessary after the rides at the data center, but
The position of that bar, is it at like the front side of the rack along the...
so it actually it's in the front and kind of the 2/3 of the way back. So it attaches both to the front of the rack frame as well as to the back.
So there's some diagonals going towards the back post as
No,
well?
it's just, I mean, we could, but we haven't had a need for it. From a structural standpoint, front and back have really needed that in that particular frame or in that direction. It's really just, it's just bowing this way due to shock. Gives the shock power. It might be a bit better. Yeah, kind of. So, you can imagine a little bit here. But the front one is behind these two green bars. So the bar actually sits on the kind of the middle of that column. Right? So the first half of the column is where the cables are sitting. You got the structural part where the IT gear integrates to the rack. So that's where that front bar sits. So it's
In between the two
it's
components.
basically the same plane where the IT gear would sit. And then the one on the back sits, again, kind of in the middle of the,
So it's behind the wire manager, right at the beginning of the front post.
yeah, exactly right. And then the one on the back, kind of some location in the back. So it also, so if you do like a cross section where you're looking down on it, it sits right in the middle of that the rear two posts as well. Kind of the shadow as you slide. And then there's also a third piece. There we go. So there's also this piece back here in the back. So that piece provides structural support for the bus bar cage that's running along the entire length of the rack. Even though the bus bars themselves, on the location, are broken into two separate zones, the cover piece that protects the bus bars, as well as the people that are using the gear from the bus bars, that is one continuous piece that goes from the top to the bottom. So that third piece that's behind that bus bar cage and provides some horizontal stability to make sure it's in the right spot. Yeah.
Isn't the height used creation?
So this rack is actually, it has more weight to it. So even though it's taller, it has more weight to it. It's actually performing a little bit better than the traditional open rack E1. Some of it probably has to do with the fact that the bar that was really the primary failure mode that we were seeing during transport was definition of rack. Probably mostly from forklifts. Gear up and dropping gear on the forklift. That's where it is. The definition around. On the whole, the fact that it's higher and heavier, that's performance better. Any other questions? Sure.
I don't say it, no, it's not that important.
I'm just saying nothing's gonna fall out of the sky.
No. But anyway, just, once I've done something, I don't have to do that. That's your problem, all the buildings. Right.
So we have, I guess, choke on the output plate of each of the power supplies, as well as a clip that goes for all the IT gear. It also has another choke on it as well. And then the other thing is that since the two zones are electrically isolated, so it reduces the noise voltage. But we haven't incorporated our problem yet with it. Like you want it to be fine. Yeah, so we do like standalone and do rack level testing. Fine.
Yeah, there's also a choke inside of Cubby as well. Chassis that's that interconnect the bus bar has yeah. Okay. Yes. Then you're right. You're in the right spot.
Okay, great. No, I didn't know how far that back.
So, as I mentioned before, the PSU itself is 96% efficient from AC input all the way to the 12 volt DC. Whereas, let's say high voltage DC, that part, the DC-DC part from river voltage to the 380 volts DC might be 98% efficient. But there is that backside where they can take down where they convert the AC coming from utility up to 380 volts. So if you add those two or multiply the two efficiencies together, they're almost equal. So the power, the way the power architecture is, utility comes in at 110 volts, 110 kV, gets set down to 12.5 kV, and then from there it gets goes to the transformer, gets transformed directly to 48277. And then that voltage directly goes into the input of the shelf. So this shelf will take the 48277 three-phase input direct to, and then it splits it between the three power supplies. Each one gets one of the phases. The input to the PSU is direct 277.
What do you do?
Yes, the moment you have a failure, if one PSU fails, now you have a loaded balance in the line. They'll get everything. Yeah, so for example, as Renee mentioned, copy, or in V1 we had each IT put for the server, storage, and all that. They would have a control as well. So this way we reduce all the noise, all the different acts.
Yes, yeah, so this is the V1 clip. It's out on the open rack under the specifications download the 3D file specification. And there will be a clip as well that'll be submitted as well.
V2, I don't, right now we're not used to this.
It is slightly different. So it'll take a little bit more current on V2, and it's also slightly smaller. So the V1 clip required about 1.5 OUs tall in order to fit it in. So the new one will fit inside of a 1 OU elevation. So you're pulling more current through this smaller frame size. The clips themselves are very, very similar to each other. One was for cubby, right? So we wanted to minimize the elevation so we could maximize the amount of airflow that we get on top of it, as well as just the volumetric that's available for you. So that's one of them. Two of them, kind of a second driver was the fact that we've got the open compute switch project is now running, and so eventually some of those could also be 1 OU tall. So we need to kind of enable that as well. So the one that will be submitted looks like this. So it's got one clip running off the bus bar that then splits that input to 3 separate outputs, so that you can run it to 3 separate nodes. So this is the one that will be submitted. But so if you wanted to say a switch or something like that, it needs only a single input. So you could basically follow the rest.
You know, the design rate for 150 amps input, okay. And 150 amps input.
You want it 100. 50% more power.
Standard defines the interface.
Yeah, exactly right. So the either clip, yep, same size bus bar, no change there. So basically, it kind of goes back to the point I made earlier. Any IT gear that was compatible for OpenRack V1 flip onto the bus bar, all of that is controlled by the standard. Yes, if you choose, you don't have to use Cubby, but if you choose to use Cubby, it comes with a slightly different IT node or slide or whatever you want to call it. So Renee showed that as well. There's a sorry? Yeah. Yeah, there's no logic built in, so there's still some manual processes involved. Where it is.
I don't know, I decided to put it
Yeah, not just yet.
Just one thing that I might have left off to add is in that communication section, the RS-45 output we had out, coming out of the shelf, we'll be able to read the input voltage, the load. So the shelf is, each PSU is pretty smart and it will send out the information. No, it's completely dummy. All the smarts are inside of the PSU itself.
So the reason they're embedded inside the PSU is because that's very easy to service. Right? Well, the PU is more difficult to service. So that's why it's dumb as possible, so there's as few failure modes as possible. So just easier. Yeah, put as much logic as you can there. Sorry?
There's no monitoring the PDU, and historically we've never had any monitoring in the PDU, but in the PSU now we can monitor the output load of each PSU, the input voltage, different failures, what failed, the failure status. We can record, or we can find out if the battery's being charged at that moment. So there's a lot of information that we can find from PSU. Yeah.
So I guess like, you're looking at the market sell that. That was how it's happening.
So the PDU is completely dummy. So there's no, the PDU is dummy. There's no power cycling. There's no voltage or power reading. It's all inside of the PSU. So this is the first time we'll have the ability to do it. The new one, the shelf was dummy. It didn't have any communications in it, so we weren't able to do anything we wanted.
David, like, power shelf came out as a power shelf. I know this has soft controllers in it. That is commercial. And so one of the things we can do is through the BMC, we can tell them how much power cycle. That can reduce the BMC, so it drops the battery. We can roll the power cycle, or we can roll a technician battery.
Yeah, so I think you're referring to the RPB, so it's in front of each row. And its main function, it's to clean up the power, but also limit the short circuit current for that row. So we'll be using that same one in the rack because it's already built into that row. So the V2 will be connected to that bus bar system that goes to this RPB. Just an inductor. Yeah, just a large inductor.
Hang on one second. June, you got a question.
Two other charges that are, that's
which kind of practices? Sure. So, yeah, right now we're not implementing that on most of our gates. I think of one where we've actually implemented it for V1. So V2 is still really we're all. But like you said, there's lots of information out on the website right now that shows the simulation data.
Yeah, so the PBU, there is the EMS, SM1 inside of the, so we can do all of that. Temperature, all the smarts are basically transferred over. Yeah, so we're presenting next on the PBU itself.
Oh, there.
Yeah.
Why don't we let,
There you go.
Do we want to take a 10-minute break? We're actually running 18 minutes ahead of schedule.
Yeah, there's
So,
So 18 minutes.
yeah.
all right, then we'll let Zeb talk.
I'm just trying to ice him out, right?
Yeah, right.
And the B2 power supply and shelf spec is already out on the website. I suppose more in detail about the spec that we give the vendors to build. So on the website.
Yeah, we can come back at 2:30. Well, we'll start right on time, right at 2:30. Wait.
Oh, you gotta hit, she wanted to turn it on.
On a mute first.
All right, so Joe's gonna go through the BBE portion of the PowerShell real quick.
So I'm Zoe, I'm hardware engineer at Facebook. I'm going to be talking about the battery backup unit with lithium-ion battery. So I'll quickly talk about the V1 approach and what it was. It's been pretty much what we just talked about with the blue battery cabinet. But it's important to actually understand the use case of our BBE unit. And then I'll start talking about the lithium-ion battery approach, what the design is, safety. The safety is pretty important with the lithium-ion. And we'll go over aging and state of health tests. So, battery cabinet. So this is what everybody was just talking about just a few minutes ago. At Facebook, we got 480, 277 coming directly to our power supply. Power supply connects that AC and provides 12 volts to the motherboard directly. If that AC goes away, we jump in with a 48 volt DC. We cover that AC loss until AC generators kick in, and we wait for the main AC to return. That's the blue battery cabinet. What it is basically 5 shelves of lead acid batteries, 4 lead acid batteries in each shelf. So there's 20 of them there. They're all sealed, valve regulated lead acid batteries. The cabinet itself can be 56 or 85 kilowatts. It's a 277 three-phase input. Got 3 rectifiers for charging and to power some IT equipment that we have, like switches that need DC voltage. And we have battery monitoring, standard lead acid battery monitoring with this cabinet. We have the impedance, voltage, current, and whatnot. And it's designed for a 90-second backup. And I'll talk about that in a minute. What's inside is pretty much beefed up car batteries. In each battery, there's 6 cells. It's 12 volts, pretty standard, and standard impedance. But one thing to take away is that each one of these is 38 kilograms. So just imagine, and that's about 84 pounds. Imagine trying to put 4 of these on the bottom shelf on that cabinet and 4 on top on the 5th level. So our use case for the 90 seconds, as we've been talking about, it's in 2 cases really. One is when the AC outage happens. We're on the main AC, outage happens, AC goes away. The battery kicks in until the generator for AC generator turns on. We need about 20 to 30 seconds. And then we put some forgiveness time in there and make it 90 seconds just in case. And then in case 2 is when AC actually returns. We need to switch back to the main AC line. So we're on generator, battery kicks in, we go to AC when it's main AC when it's stable. So that's the use case for our battery units. We're not operating on batteries for a prolonged period of time. 90 seconds max. There's actually, as Samir mentioned, there's a firmware, the firmware in the power supply times out after 90 seconds. So it's not even possible to surpass that 90-second timeout. At that point, when you hit 90 seconds, power supply will turn off. The whole system will turn off. Yes. Absolutely. So you're describing a case where you have multiple outages at once, for example. So the use case that we're going after is from what we know from our data center. And we know in our data center that it is guaranteed that the first generators will kick in about 20 to 30 seconds. And if they don't kick in, we have backup generators that will kick in within the next 20 seconds. And if the main generators and the backup generators fail, at that point we're saying, you probably don't even want to be on DC backup because there's probably something fundamentally wrong with what we have in the data center. So when we time out in that scenario, we're fine with it. And we're actually looking into what's happening and how we can fix it.
So what is the, I'm assuming you guys have a minimum recharge duration so that case 2 can't happen until there's been a period of time since case 1 back online.
Absolutely. So the design we have right now is severely oversized. We have like the power supplies, we have the N+1 redundancy. Each battery is 3,600 watts as we get into it. So 90 seconds for these batteries is not a problem at all. They can withstand up to 3.5 minutes if you wanted to. So having one outage or multiple outages is fine. But when you actually start looking at the lithium ion, it's not how much power it can deliver, because that can be very variant depending on what age of the battery they are. But it really depends on all the conditions around the operation as well, like temperature, for example. We don't want to be operating the batteries multiple times because we'll reach some temperatures that we don't want to reach with the lithium ion. So it gets really complicated from that perspective, and that's where the safety mechanisms come in. But in terms of the capacity itself, fresh batteries have no issues handling multiple outages and multiple switchbacks. By the way, that switchback, that switchback happens in less than 10 seconds. Okay, so when the outage happens, and we go to AC generator within that 20 to 30 seconds, and let's say it's even longer to 90 seconds. The only way we go back is if the data center checks and makes sure that the AC is stable for a certain period of time before they turn off the generators. And that check will include calling the utility, just running on the main AC for a little bit of time, making sure it's stable before we actually go back to main AC. And this is dependent on region as well. In Europe, data centers is a little bit different because those guys have redundant grids. In North America, there is more emphasis on the generators and the backup generators.
Switching over we'll know how long we start.
So this is the diagram from before. We were trying to get rid of the battery cabinet, and we talked about the benefits of that, giving space back, but space is really not a huge win. From my perspective on the technical side, the distribution of DC from that battery cabinet to 6 racks was actually a lot of copper that we had to put in. So we got rid of all that. We actually took the battery and put it inside the shelf. It's right next to the power supply, so we don't need those hefty copper cables running across 6 racks. And the other huge win on the technical side is all the air that was escaping through the battery cabinet, the cold air. You saw the battery cabinet had all the holes in the front, and that was kind of an outlier in our cold aisle because all the air was escaping from the cold aisle to the hot aisle because of this battery cabinet. Now we don't have that anymore. And as we quickly talked about, we're having a slow transition between actually populating that one space because of how the data center folks were used to that slot being for battery and battery specifically. So the space for me is not a huge win. The win for me is on the technical side, on the electrical and the thermal side. Yeah. Actually, it turns out the cost of one battery cabinet is slightly more than distributing the batteries into the rack. So with all the cables removed, all the bus bars inside the battery cabinet removed, our target was saving at least 10 to 20% cost. And we met, I wouldn't say we met the 20%, but we met the 10% cost target. So it's actually, even in terms of cost, it's more beneficial to use the lithium-ion batteries in this, even though it's severely oversized in our scenario. So with that, we'll jump into the design itself. So the goal is to get rid of the lead-acid battery and use this. This is pretty much the cells used in Tesla, for example. They're 18650 cylindrical batteries. For those of you who are familiar with batteries, 18650 refers to the size. They're 18 millimeters by roughly 65 millimeters. They are nominal 3.6 volts, maximum 4.2, 2 amp hour batteries. It's pretty standard. What's not standard about them is that they can be discharged up to 30 amps maximum. And they're 46 grams each. So if you actually multiply that out, it's 14 kilograms per rack worth of batteries. That's lighter than one lead acid battery. Because of that, they're actually thinking about integrating batteries in the data center as opposed to shipping with batteries inside the rack. It's so simple. Just slide it in, it's very light. And with most lithium ion, there's no memory effect, unlike nickel cadmium. So you don't have any memory effect issues, and the voltage curve is pretty flat. Our cell is, so there are three major components to a cell. There is cathode, anode, and the electrolyte. The anode is pretty much carbon on copper. The electrolyte is the secret sauce between different battery vendors and what they use. It's usually lithium salts. And the interesting part is the cathode. Typical batteries are lithium cobalt. That's what we usually hear when we hear about batteries for cars, batteries for laptops. And cobalt really delivers that high capacity that we need. Problem with it is that it's not really controlled. When you discharge lithium cobalt batteries very quickly, in our case, for example, high current in 9 seconds, you have to control the temperature somehow. And mixing it with other ionic metals like nickel and manganese helps with that. So one recommendation from our part is if you're actually going to use lithium-ion batteries is really understand the cell, understand the chemistry, and know what the use cases are, because the cathode can change very dramatically in terms of chemistry. The pack uses 52 of these cells, and they're arranged in a 13 series 4 parallel configuration, so 13S 4P. We charge each cell to 4.0 volts, and that translates to about 52 volts on the pack. We set the charger on the power supply slightly higher than 52 to 52.5, just to compensate for the losses between the cables and whatnot, cables and connectors. And if you recall, 30 amp each, they're 4 in parallel, they're 120 amps max that you can get out of the BPU. Each one is 3,600 watts, each module. That's 300 more than the power supply. And the reason for that is because of all the efficiency that you might have when you actually take power out of the battery through the power supply to the motherboard. And each module is 5.2 kilograms, so weight-wise, huge win. And that's roughly how it's arranged inside the BBU. There are 2 levels of cells, and they're stacked on top of each other and next to each other. The shelf, we looked at this picture in the previous presentations. It's a master and slave between the power supply and the BBU. While the power supplies can talk to each other, the BBUs can't. And the BBU only corresponds to individual power supply. So the power supply fails, you actually lose access to that BBU because the power supply was the master. And then on the rack side, there are 2 shelves, 6 power supply, 6 BBU, completely separate from each other. So some of the main features that this unit has, obviously battery monitoring. So we carry everything we have from that blue battery cabinet inside the module. We actually have an internal BMS for every module. And that BMS can monitor a lot of variables. Everything you can think of in a lithium-ion cell, for example. Voltage, current, temperature, can do some crazy coulomb counting, can have add rate monitoring. It pretty much follows the smart battery monitoring standard that's out there and more. And then we communicate through the power supply to the BBU, and then we can read variables through the power supply. We have active cell balancing. So when it comes to cell balancing, you have passive and active. Passive is the more traditional way that was used with lead acid. And it didn't really rely on the chemistry of the cells. With active, we're actually balancing the cells as the cells are charging. So when the charger is on, we wait for the cells to reach a certain voltage. If a cell reaches that voltage sooner than the rest, that one's bypassed, and the rest of the cells continue charging until it's full. Yes, not each individual, because you recall there are 4 in parallel, and those that are in parallel, they're basically naturally balanced. So there are 13 strings that we monitor the voltage of, and we try to ensure that they're within 1% of each other. And that ensures that the maximum capacity or the joules inside the pad is almost roughly the same every time you charge. Yes. There's only one charger input, and that's coming from the power supply. Yes. Every laptop nowadays follows the smart battery specification, and so does this. We have an automated cell health check. So with a lead acid, you can put a barometer in there, you can measure the impedance. With lithium ion, you can't anymore. So how do you determine how old a lithium ion battery is? You need to do what's called state of health test or battery test, and we'll talk about that. We have redundant safety mechanisms. Obviously, safety is very important. Because of that, we've introduced at least 2 layers of safety. So we can have, and they're completely independent of each other. So you can have a mechanism fail, safety mechanism fail, and you have a backup for it. The fact that we're going through the power supply creates some sort of free safety mechanism for us, because the power supply is actually monitoring the BBU, and it knows the state of the BBU. So it can actually cut off access to the BBU if there are failures. And if you've noticed here, I have a module here. It's a fully enclosed module. There are no fans, and there are no holes. What we actually saw from our testing was that in the worst case discharge possible, that means that we've lost redundancy, and we're at maximum power on the rack. We're actually seeing only a delta of 25C increase on the cells. Then we looked at the probability of us having that scenario happen in the data center, and it was pretty low. And we looked at what the temperature range is that the cell can deliver. And we saw that we actually don't need cooling for these, especially for the 9-second operation. 25C increase is really not that noticeable when you look at the range that the cell can handle. And in a normal case scenario, it's even much less than that. It's about 10 to 15 C increase. And having it fully enclosed actually is another plus. It's a safety plus. If something were to go wrong in there, it's fully enclosed. There's no fans blowing unwanted debris and whatnot on other parts of the shell. Yeah, so we can talk about that right now in safety. Any questions so far? It's irregardless of the ambient, actually. There's very minor effect on how the lithium ion discharges depending on the ambient. Although, when I talk about ambient, I'm talking about this case, but it's 18 to 35. Of course, if you go to 60 C and start doing discharge, then it's a whole different ballgame. So, safety. So, battery modules are one of the products that you have to watch out for in 2 aspects. Usually, during operation, you need to watch out for electrical. Battery modules, you need to watch them when they're just sitting there, when they're being shipped, and they're being stored. So how we approached this was we made 2 major buckets for safety against shipping and storage, and during operation. And then we started thinking about the areas where failures can happen and what can go wrong in itself, trying to understand what happens. So in shipping and storage, you can have shock and vibe. You can have over temperature in your storage room, for example. During operation, you can have over and abusive discharge, and you can have over and abusive charge, you can have over temperature conditions, and whatnot. We spend a lot of time trying to understand what happens when over discharge occurs on a cell and overcharge happens in a cell. And what really came down to was that what safety mechanisms does the cell itself provide? Because you can only have so many electrical safety designed into the EBU. And that's what we're going to talk about. That little box in the middle is the UNDOT, and UNDOT basically sets the standard for transporting lithium-ion modules or lithium-ion products. And that standard actually touches both operation and shipping and storage. But I would say that sets the very minimum that every module needs to meet. It's a certification that every product needs to meet. But in my opinion, the way the lithium-ion is designed right now is you need additional safety features included. So on the cell side, we have 3 safety mechanisms built in. And it's really hard to find a cell these days that doesn't have these, actually. So in the cylindrical cell, you have the top and bottom, plus and minus. And then you have the cathode and anode that we talked about. Between those, there is the separator. The separator is the first level of protection. The separator is usually a thin film that the ions can travel through. But at a certain temperature, at high temperatures, this thin film, depending on the vendor on the battery, can solidify and stop the ion traveling from one side to the other. So that's one level. And then what you have is a CID, or a current interrupt device. That's pretty much a fuse that you have inside of the cell. If the electrical conditions inside the cell are surpassing the spec of the cell, that little piece will open, that little fuse will open, and will create an open circuit in the cell. So it becomes an open circuit and you can no longer use it. If you have pressure buildup, because this is a chemical entity, if you have pressure buildup in the cell, there's a similar protection that's called the gasket. It's the gas release vent. That opens, that also creates an open circuit. It's more like a fuse, but in a mechanical sense. On the pack side, we have different kinds of electrical safety. And this is, I realize, is a very detailed diagram, but what I'm trying to show here is how we actually approached it. We categorize normal protection, primary protection, and secondary protection. The normal protection are fuses, switches, and whatnot that you see in almost all electrical products. So for charging, we have charge FETs, those are their switches, and then you have charge fuse and a discharge fuse. And one thing that I'm not showing here is electrical fusing. That's highly recommended on our side as well. Some sort of controlled fusing design in the pack. And then primary protection is what the BBU can offer for its own, and it can communicate out. That's the micro it's got. It's monitoring RS variables. It's got thermal sensors. It's got cell balancing, ensuring everything is within range. And it can send signals to the power supply saying, stop charging me, or stop discharging me, stop using me. And those are usually digital, translated by an analog signal between the two power supply and BBU. On top of that, we have analog, strictly analog signals between BBU and power supply. For that, we have internal voltage sense directly as the BBU sees, directly connected from the BBU to the power supply. And we have temperature sensors set at higher limits than the internal to the BBU. And those are connected directly to the converters of the power supply, and they can stop the power supply from using the BBU quickly. Other configurations, definitely possible. We were shooting for about 52 cells because of the dimensions. The BBU is slightly shorter than the power supply. if in case in the future, we're actually discussing now if we need more power, then we'll think about actually doing 13 as 5P, 14 as 3P or different configuration. But it all depends on the cell that you're going to use, the arrangements we're going to put them in, and if they need special thermal design and whatnot. The easiest way obviously would be to get more powerful cells and just swap them with the same form factor and swap them with what we have right now. But I think we're reaching the limit with this cell technology in this form factor. So in the future, we might have slightly bigger cells, maybe in the same 13S order. So aging. So we designed the module for a 6-year life operation, so 6 year until end of life. And we designed that for our use case. This will be very different in different use cases, so special attention must be paid to that. So our use case is 18 to 35C in our data center, and then we do a maximum of 1 discharge per month. And that we get from statistical data on how often we actually see outages in the data center and how quickly it returns and whatnot. And also shipping and storage definitely matters. Storage temperature actually directly affects the aging of the cell, so that needs to be also considered. So with aging of the lithium ion, there are two aspects. One is the increase in internal impedance, and the other one that's often not considered is actually the capacity loss. We expect 20% increase in the impedance and 40% decrease in the capacity. So right now we're shooting for 90 seconds, and new cells can deliver 3.5 minutes. So basically the correlation would be what the effect of that 20% internal impedance is on the voltage drop and the 40% decrease on that 3.5 minutes that we have right now. And we think that within 6 years, given those conditions for temperature and aging, we'll be able to sustain a 90-second backup with no problem. Yes, I would say even less than that. Yes. We actually have a recycling team at Facebook, and we work closely, and they're right now dealing with the acid ones, which is much easier than getting the little lithium that's in here from each cell. We're working with them to actually put proper recycling procedures. So the battery test. Again, how do you figure out how old the lithium-ion battery is? You have to discharge it. There's no way around it. You have to do a simulated outage and figure out what the battery can deliver. And to do that, we do state-of-health tests. And that's done randomly across modules. We don't want all the modules to do them at once, because in that case, we might lose redundancy at the time we're doing it. So in one shelf, we only allow one BPU to do it at one time, at any given time. And that starts randomly, based on a random number that's actually implemented inside each module. And it repeats every 90 days. There's no real science around how often we do it. We just took into account the number of cycles each cell can do. And so 90 days sounds like a confident number in terms of when we feel comfortable that the cell can deliver the energy required and how often we need to check. And we need a certain discharge on the cell to make meaningful data out of the discharge we get. We only allow the battery test to be done when there's at least 1,500 watts on the rack. That, again, comes from our statistical data. When we think about all the racks, we see that there's usually, in most cases, at least 1,500 watts per shell in a rack. So we're very confident that that condition is going to be met in our case. And what's interesting about our SOH test, if you actually, when we started looking into how to do battery tests a couple of years ago, everybody in the industry was discharging their battery fully, up to 80 to 90% discharge, and then they would let this OCV time, where it's open circuit voltage time, and then from there they can determine how much the internal impedance of the battery has increased from what it was before, from the previous test, for example, and how long it takes for it to stabilize. And then you can do capacity calculations and the impedance calculation. But in our case, if we're doing 80 to 90% discharge, that basically means that we're depleting the battery. And that would translate to you don't have any redundancy on the battery. We didn't want that. So we actually changed this slightly by actually only doing 30% discharge on the battery for each test. That would ensure that during or after a test, you can have an outage, and the cell can sustain that outage. And the way we could actually achieve this was we had to redefine how we do impedance calculations and capacity loss calculations. We actually had to go, instead of voltage-based, we have to go voltage and power-based, we have to go to energy-based. And the way we can facilitate that is we have an intelligent power supply. We know, we have an intelligent power supply and a DVU. We know the voltage, we know the current, thereby we know the power. And also, because of this intelligence, we know the time, so we can actually do energy-based calculations. Yes, once every 3 months, I would say that we do. It can be. We've designed it so it's invisible to the operation. So it's not disturbing. To count the discharge as a battery test? Yes, we do. Yeah, yeah. That was actually that's a great point. We actually, because of this new approach, the 30% approach, one discharge can be equivalent as a battery test. So if the battery is actually asking to be tested and a discharge happens, we'll actually try to use that data to do the calculations. And if you can do it, and it's a successful test. If not, now you nail it to the last unit.
Use that energy, but if for example, circuit, now the power supply is really much powering load cell, then instead of the AC current, so the external power, right? So not wasting the power. The energy is just swaying back. So you just have a further that one battery. There's no waste.
All right, our next next presentation starts at 4, so that gives us a good 50 minutes to kill. So I know there's some other people that want to come see it, so you know, start early. So fortunately, if you guys are off for about 50 minutes when we start again at 4.
You're live.
All right. So the next thing up we've got on the agenda is kind of a review of the differences or changes between the Open Rack standard 1.1 going to 1.2. So I'm not going to look at all the stuff that's in the standard right now. I'm going to look at 1.1, only what's changing between 1.1 and 1.2. So kind of the goal is to kind of present this in its final form and get feedback from the community to see if there's any additional changes that need to get made before it gets presented to the incubation committee for final approval. So a lot of this stuff's going to be fairly detailed. The mechanical stuff will go pretty quickly, but there's quite a bit related to power we'd like to get you feedback on. So a lot of this stuff is driven by feedback from the community. So this is just one example of it. So there's a statement there that the rack must be able to support 3 bus bar pairs. Only one of them is wired. So this simply states that if there is only one that's in the rack, it has to be in the center. So this is something that's actually stated further on in the specification, but we're adding it into this portion as well. So something else that's been added, this is really more of a clarification than anything else, is where the OpenU sits in the rack frame relative to the features that are in the rack. So this just kind of tells you where a theoretical OpenU sits relative to the frame. It's not actually a new requirement at all. It's purely information. So this, however, is new. This is something I think we started talking about last year. So what this does is it identifies the location for a voltage connection between the power shelf, like what we see up here, and the bus bars that are sitting in the back of Open Rack. So we'll look at the text here in a second. But what we start off with is basically a minimum of 2 voltage connections, and then from there it'll scale up to 4, and then 6, and then 9. So depending upon the power that a particular customer wants to populate the rack with, whatever power density you're working with, you can increase or decrease the number of voltage connections that you've got on the rack. So the Open Rack standard doesn't set the size of the bus bar. Right? It sets the thickness of the bus bar, but not the depth. So this gives you the ability to increase the depth of the bus bar to increase the amount of power. If you want to add more copper, you can be more efficient, or you can still pump a lot of power through a very small bus bar and be less efficient. It's totally up to the designer to choose. And this also gives you the choice of how many voltage connections you would like to have as well. So there's 4 different colored squares. It's kind of hard to see, but there's basically 2 that are inside the black, 4 red, 3 inside the blue, and then 9 inside. So this is what the actual text says in the standard. So I hope you guys read it. But, what it states is the quantity of voltage bus bar thing does rack variable power. And then it defines this location on the bus bar relative to one of the rectangles that is used as kind of a vertical datum in the rack. So it doesn't necessarily tell you where in the rack it can be, right? So if you have 1 power shelf, 2 power shelves, 10 power shelves, you can put these wherever you want. It doesn't matter how tall your power shelf is either, right? If you have a 1 OU power shelf, you can slide this in. This just tells you where the voltage connection will sit relative to the queue. What this will do is allow you to have kind of standardized location for the way that a power shelf would interact with the rack. This also it specifically says bolted connection. So for some reason, somebody wants to go out and create a hot plug clip version of the power shelf that just stamps into the back power the bus bar on the back of the rack, that's perfectly viable. There's nothing in here that would prevent somebody from going out and creating that or some other clip or whatever you want to do. But if you want to make a bolted connection, this is the way it would be done.
So I get the 4-hole, the 6-hole, and the 9-hole.
Sure.
Seem pretty straightforward. The 2-hole, does it specify that they must be the left two, or could they be the top two? You're picking them vertically, but
yes.
could they be the top two horizontally?
No, they have to be vertical.
Okay.
So
is that based on surface area vertically?
So one, if you are using only 2 holes, assumption would be you probably have less power in your rack, and therefore you potentially want less copper. So if I go depth, then that you're kind of forced to doing like a 45 millimeter deep bus bar. So in order to at least give you the option of having a skinnier bus bar, 30 millimeter so deep bus bar, that's why the first 2 are vertical.
Yeah, I was just thinking from like a 1 OU power shelf option, and then wanting to made with the bus in less than a 1 connection, that they might want to have the option to go horizontal to they were restricted vertically.
Sure. I'd have to go back and check, but I'm pretty sure you can get both of those inside of a 1 OU layout. It's a 25 across. And we're using M8 bolts. That's 16 plus maybe your washer. Your washer's 20, so it's 45 out of 48. So as long as that's centered correctly, you could actually use both of those in a 1 OU.
Okay.
But that would be something I can double check and make sure.
I'll go look at ours too. We have 2 connections. I'm pretty sure they're vertical, but I'd have to come back.
Okay. Are they? Do you know if they're 25 millimeters apart?
I don't. I can't figure that out though.
Okay. So the 25 millimeters comes mainly so that you've got enough, trying to maximize the surface area in between those connections. Particularly when you go to 4 and you're trying to go north and south on the bus bar, right? You want to make sure that you've got enough copper on that bus bar so that you can distribute it nicely. Otherwise, you're going to have real high voltage drop if there's not enough copper in that connection.
And that 25 millimeter spacing is consistent across all 9 of those positions.
Yes, it essentially defines a matrix starting with that very top hole and then goes out by 25 by 25 grid. So this is actually what it states up here. So that might be something put into here as well. Hey, well, would you mind taking some notes for me while I'm up here? Yeah. So why don't we add onto this as a requirement under additional locations. It follows the 25 millimeter grid. It states it, but put that as a work requirement. Okay. If you also take a note to have me verify that that will fit in a 1 OU power shelf. I'll go double check that. Been quite a while since I've done that. So the other thing that's important to note on here is that we're using M8 screws to make that connection. Stainless steel. That's the hardware is all stainless steel.
Is that specified by the standard as well?
That it's stainless steel?
Yeah.
Yes. Yes. So you can actually see there where it's calling out data needs and made stainless. So again, that size that inmate size is selected, so it's not so large that you're cutting out too much copper in the bus bar, kind of balancing that with the ability of that bolt to clamp. You want to make sure you get a really good clamp between those bus bars. That's where you're going to get most of your loss. Really between the power shelf and everything else, it's all going to be through that connection, right? The IR losses are really, really small compared to the losses associated with going across the bus bar to bus bar. So any questions or additions, changes, recommendations? I'll go on and go to the next one. So this is just a minor tweak. This there should be a 2x in there. That was something that was found several weeks ago. So we'll add that onto figure 8. Okay, so this next section is the power section. So this is a lot more dense than the mechanical stuff. So there's been fairly significant changes related to the power section. Related to the standard to really expand and clarify this section requirements. So this first page, that first paragraph really is not any different than what's in the report, but it's included just so you can just kind of see what the context is. Bus bar is essentially going to have a 12.2 volt plus or minus 4 EC. So that's the requirement. So the way the standard's written out is anything that's a shall is a requirement. A should is kind of nice to have. It's also another level where it just says recommend. So in this case, the 12.2 is the requirement that you really should have somewhere between 12 and a half plus or minus a little bit higher. There's also a statement there around the capacity of the bus bar. That's should as opposed to hard requirement. The last set, bus bars and open rack shall not be electrically connected to racks of metal frames. Have positive bus bar connected to chassis ground, or have negative bus bar connected to chassis. So this is to eliminate ground loops. So really, it's just that second paragraph. Unless somebody has concerns with that, we can go to the next one. So this is 4.2. So this is relating to the bus bar connection itself. So this is the cabled interface between an IT node, between the IT gear and the bus bar. So this is not between the power shelf bus bar. This is your server storage element connecting on the bus. So this is pretty much all new material. So one key clip, any 12-volt power clip that connects IT gear to the open rack bus bar shall provide a minimum of 3 mm horizontal float direction. Bus bars in the back. So this basically ensures that you can hot plug the bus bar without damaging either the bus bar or the clip itself. You provide a minimum of 1 mm vertical hook height here in the bus bar to reduce the movement of the clip relative to the bus bar here in the train. So what this does is it prevents damage between the IT gear. Once it gets flipped on the bus bar, it moves vertically. If there's no float vertically in the connector, you can potentially you'll rub on the bus bar and potentially remove the plating between those two elements. So this could happen when you're in the data center, right? If you have vibration on the floor, something like that. Particularly for Facebook, since we integrate the IT gear into the rack prior to delivery to the data center, right? You're going to have that whole transportation, whether it's planes, trains, not automobiles to the data center. And what this will do is prevent that vibration during transport from destroying the bus bar and or the clip before it gets. Very important that it floats vertically. The other thing it needs to do is it needs to ensure that the negative bus bar makes electrical contact prior to the positive bus bar. So this is important because we want to make sure that everything's grounded prior to energizing the system. So the bus bar systems right now are already designed with a 2.5 millimeter offset with the negative bus bar bundling forward of the positive bus bar. So that's already built into the design of the rack. We just want to make sure that anybody that's designing the clip design where the clips are parallel with each other. We've already had one that had counted for that 2.5 millimeter offset for us. But at that point, then both of them are touching at the same time, which is the whole purpose. So, just kind of clarify that you really don't want to do that. You want to make sure that your negative bus bar touching first before the positive makes contact. And the last is there's nothing new about this one. This is already the standard, but it needs to be plated with either silver on top of a tin. And this is just to maintain a certain level of efficiency. Make sure that your power drop is not too high to the contact, as well as to protect the power.
Do you think there's a need to specify a maximum float, either the vertical or horizontal spec?
So you could certainly have too much float if the connector isn't designed to accommodate that much.
Yeah.
So I'm not sure what that would be because I think the fact that it states that it has to mate, I can't remember the text exactly, to ensure that the connector mates the bus bar and the rack. So it's entirely possible that you could design something where it have 6 millimeters of float. That would be fine as long as you can figure out a way to make sure that you are properly aligning it prior to it hitting. So I think you could pick probably any number, and I could come up with a way to make sure that it's properly guided. It just means that you may have to have a lot more depth to make sure that you can gather it up before it makes it.
Yeah, I was only asking to avoid damage on installation.
Right. So as long as you can make sure that the connector is all the way to its maximum, it's still mating. Good. In fact, more would be better, right? I just don't know what that maximum would be. Okay. Any other concerns with what's up here before we move on? I'm sorry? So the bus bar factor goes back. So there's not a lead-in per se that's defined within the stamp or anything, but there is a 0.8 millimeter radius. So that's somewhere between 1 and 0.6 is pretty much standard across the industry. A lot of you use a very common bus bar. There's also, at least on the connector that Facebook developed, there's a lead-in on the clip as well that helps to make sure that everything's on. Okay, so this is requirements specific to the IT gear itself. So this really has nothing to do with the rack per se. This section, as it says, applies to just the IT gear that plugs directly to the bus bars. So there's certain requirements that are necessary to make sure that the system as a whole plays well So any IT gear that does connect to the bus bar shall include a 12-volt hop swap controller and circuitry for soft start operations, inrush control and protection. Purpose of this is to make sure that we can maintain that 12 volts on the bus bar, right? So if you hit something on there and it drops the voltage on the bus bar, you're going to mess up your whole power zone. So I want to make sure that that's included. And part of that, it needs to limit the inrush current during hot swap to less than 100% of the total load of the item. So there will be an inrush current, right, when it does make that initial connection. We just want to limit that so it stays within the range of the maximum. So it shouldn't be overshoot. Kind of the third item there is need to maintain the maximum positive and negative voltage deviations. Induced on the bus bar when you insert the single IT gear, whether it's in or out of the rack, must be within the voltage range of the 12.2 that's specified earlier. The purpose of this is to be able to take your proposed IT sled, push it onto a bus bar that's got a power shelf that's been approved, and it shouldn't drop voltage because of the requirements of voltage should still stay up. So this is more of a requirement, not so much for the rack, but these requirements should be incorporated into everything that the server and storage projects develop, right, to make sure it's compatible with OpenRack. Okay, so this is related to the noise and ripple related to the IT gear. Again, this section is still related to 4.3, so it only applies to IT gear itself. Should have enough overall input capacitance and filtering virtually use no differential mode of noise at the bus bar. With the common source of 12-volt power is not included. So this can be as simple as putting a common chokes. Just like the recommendation. It should have a 100 choke included in the IT gear. Lines if included is a really good chance of what this will do is eliminate any potential risks that somebody's design might not possibly use. You can design your IT gear without it, great, but pretty much that. Something else that's important is we need to provide a method to prevent an electrical short in the sled and cause the voltage drop on the bus bar. So essentially, using something that'll prevent sort of catastrophic failure in a particular node from cascading the rest of the power shelf. But ideally, don't want to take down the whole power zone with a short one. That is hopefully be contained within the IT itself. Yeah.
We haven't really talked about what's testable, but what's your thought on whether, as we get the requirements, whether we can hand off to the requirements of these testable devices?
So that's exactly right. So that's kind of why in section 4.3 is in there related to IT gear. It doesn't necessarily have to do anything all with the rack. Right. So kind of the purpose of all of this 4.3 section is to help make sure that this information gets pushed to those tests. Right, they're not included in the server stack or the storage stack that you just make sure they're testing. As the node done, they're validating.
Right. I'm just wondering if you want to think about limits, as far as like differential. We can chat with you.
there should be, there is a requirement for a ripple.
Under it.
But it may not actually show up on these slides because it's already covered.
Oh, okay.
So,
Sure, fair enough.
it should be under,
It was ripple from the power shelf to the bus bar. This is. It's okay. I don't think it's all right now, but you know, I think it's worth thinking about how do we measure these things? Like, what's the key measurement?
Right.
What's the range?
Right. Yeah, let's take a note of that real quick, if you don't mind, Brian.
Yep.
I know there are other ripples in there. In this case, I think what he wrote is saying virtually.
Yeah. Probably. Yeah. You know.
All right, that's good feedback. Let me, see if I can get,
They wanna also consider specifying.
okay, research as well. Okay, yeah,
Just so it's got a hit, the name on.
sure, pull that out. Sure. Yeah. Yeah, we'll definitely do that as well.
You even go so far as.
Sure. Yeah, I think, I'm not sure what I think right now.
But I think I want to say.
On both, yeah.
Insertion. Either under motor. It's very interesting.
No, that's good feedback. One, hot spot, I didn't think we're out. But, go ahead. That's better than these all apply. Kind of I here. Their touch is not far, but also when installing it. So I put that out there. Good. So max power draw, all I see here is the bus bar is out of maximum draw for us. For full weight. So basically it's saying that you've got per full width OU, doesn't matter if you've got, 10 sleds or one sled going all the way across, that total body can be more than 1500 watts per OU.
These are the most power.
It doesn't.
But 3 bus bars. That 1 bus bar can draw 1.5 from it. 3 bus bars. I can really call it 35.
What's
Your power shelf is the main load, whether
Yeah. Assuming you don't.
at least
Assuming you have a central power shelf.
right.
It's powering all 3 bars.
Yeah.
What's the bottom? I mean, I hate crap.
Sure. So this is really high. So what this does is it sets a limit for the size of the test picture that you can put on there, right? Otherwise, I don't know how big a thing I'm plugging on. But now if I say this is really pretty high, right? 1500 OU, right? Right. So this is well outside of what we're doing right now, or anybody probably can doing right now. So that's why we picked that number, because at this point it's a little silly. But you can imagine somebody storage system, or something like that, but we needed to set something that would kind of help define the on what you shoot for certain kind of maximum node of on board. So we can certainly change this to any other number, but that was kind of setting an upper bound for that. Doesn't say it has to be efficient either. That level. It just has to be
It won't be. It's probably not.
It's all fans.
Okay, so we didn't have any change to this, right? Just explanation of one. Okay. So this is 4.4, so this relates specifically to the power shelf that's getting connected into the system. So all the components that are providing the 12 volt DC power into the bus bar shall have an output voltage with ripple and noise less than 120 millivolts peak to peak. I think you might be right. Controlling the shelf as opposed to the ripple. We can add specification. Probably more to it. And it tells us we have 21.
Well, those are what the specs have for. What Microsoft gives you is per graphical and showing decay more. It's kind to have that in part of specs, so it's not necessarily permanent, but also the different ranges for the move long front, move,
Okay.
non-move. That's necessary.
Okay.
So that's actually the
No, it's like, like a military, military aircraft. It's not just the equipment level, but we can see it. Nice. Yeah.
Yeah, so in this case, it's
Right.
yeah, this is not very,
Just gonna imagine it.
yeah, kind of flat and boring.
I mean, these standards are there.
Yeah, I think, right there, I don't remember a lot of, there are a lot of nice that's why we see this.
Look, we see if there's something existing in the power industry that we can. Yeah. Yeah, exactly. Either that or yes.
Because there shall be a component of parent on the power shelf.
There's a lot of variability.
The parent. Yep. Huh? So,
I've seen a lot of
Have you guys seen those on the bus?
I think for us, we would require to design big enough for them to be like. Maybe there's one.
Right. So what kind of criteria would we use to kind of set that as the minimum bar?
Honestly, when I've seen them having a real field, they just go on there.
Right. So that's what we're looking to do.
Service are these are high section. We'll have one back.
No, it's just like just on the
Yeah.
Create enough.
I think it just begs because
Sure. Right.
we're getting more.
Right. So again, how do I set kind of the minimum? How would I determine what that minimum would be?
I would suggest to tie in with the rock road. And say, you know, speak for reflection. And it has to be good price.
Okay, so they're already doing lifetime cycles then, so we get or life cycle testing, right? Just to require that it's kind of certified by the supplier, by insurance. At the projected level for 5 years. Okay. Hey Brian, can you write that in?
Repeat that last one.
Sure. One would be to make sure that the Prairie Corps has been certified or validated or characterized or for some by the supplier for X amount of time, about 5 years. And we need to, I guess, specify the projection amount. What trees for the okay, so based on that range of load, use that kind of characterizing amount or projection. Yeah, so I can talk to you. Yeah.
That's
Okay, probably back. Like,
yeah. It was quite running by.
oh yeah. These will all go up before.
Yes.
Typically, service side, right, storage side. Not this one. This one is
Yeah.
What's the thing with the line that would be outdated quickly as pump more roll more.
well, yeah, that's why we got the maximum load kind of set for now. If we need to, we can always change it. Right now, I think this is.
So in my thing, maybe you're trying to everybody will apply. versus state. Site.
Well, they'll know the load of their PowerShell, right? Or they'll know the potential load of their IT shop, right? So I'm not telling them what to partner with, but they know what their load is. So, and you're right, it's going to depend on what load that is. They're going to have to go pick one.
Right.
We just need to pick what we're saying, right? What's the requirements that it has to.
Well, and I think you indirectly cover yourself because you're only saying 55%. You're not saying what number.
Right, exactly. Exactly. So there's some flexibility that's kind of built in there. Kind of grow. Hopefully, we won't have to make too many edits to it as we grow. It's built in. That's it. Okay, is there anything else you guys can think of that has come to you, maybe on some of the other sections or anything else?
Well,
Standard
part
one?
where you discussed the ripples, not that one time, I just wanted to see what that's it. Those, way of thinking. Correct. They're talking about the college. For all 7, like for example, your for folks who have 3, Ireland, if you mentioned ripple right at the node of the bus bar.
So this is the PowerShell, right? So this would be between the the bus bar.
Right? Wow.
That's all we care about. We don't know what is out here, right?
But that one thing is important. That's stressing. There's a spec today for each tracking mark. Now they're saying you go 3 together, 1 1
or 7 or 10. I'm not telling you how many power PSUs or.
Was there any other comments?
No, that one's actually been 120 millivolts peak has been a standard. I guess that was added in 1.1.
Well, yeah, but it's a standard for individual operating. It's not when you're getting it together like
for the PowerShell.
Right?
The
So
PowerShell.
I'm thinking maybe either that's too aggressive or that's too. Because like what I said earlier, when you talk about PowerShell, there's no
Right.
all the different items now are on that thing. So if you don't prevent these kind of actually it's almost like a man, we call it black man, so trying to fix. I mean, it can be detrimental to the home. Because the current infrastructure has to be addressed in each individual OEM box. So that's the 14.
Right.
When you now have a rack with a bus,
Right.
now add that node to the common to all the different IPs. If there's 84 of them on that rack, whatever the node sees, all 84 of them, there's a sensible thing that's not good. No, if we don't do due diligence, each of those can go down. Just you not address it, and this kind of ripple is very cumbersome to address. When now we have people to know them versus.
Well, so this is relating just to PowerShell, right? So all
all
the nodes.
I think you missed the IT one though.
Yeah. So it's also included in IP portion as well.
Well, I understand, but it's when you interoperate the whole infrastructure.
Right.
I mean, it's either you take care of it. I mean, my point is, these are in different things.
Right.
So we're taking care of it from an IT side and the PowerShell side.
Right.
Question is it enough? I mean, with the base system we have today is reference to the success for the base system.
Well, it's not just us, right? There's lots of people.
Because you have the actual production level solution working today.
Right.
But you know.
So I mean, this 120 millivolts. That's only 10% of the range of the spec. Right?
Well, it is, but in some applications, that could be
10%? 1%, 120 millivolts. No.
I mean, you go to, if I remember right, 6,000, like, that 120 millivolts. To that extent, I mean, seriously, that's why this interoperability opens. I mean, it's what we used to pay for. If you remember, why do you have to pay for such a high? Why do you have to pay for such an expensive storage plan? They spent many money, time, and effort to address what the issue is about.
Right.
And that's where I'm passionate about it, because I spent a lot of my career there.
Right.
And
So when the labs do the testing, right, when they're trying to validate that a particular node is compliant, right, they'll adjust it, right, the voltage up and down within the spec, right, and they can hit it with this, and it would still.
well, yeah, but
you're
it's
allowed
not
to
that-
have.
It's not that simple when you now have an open loop. I think it's plugged by everybody else.
Sure you do.
Why?
Because this 12 volts gets regulated down to 1 volt, 0.9 volts, 0.7 volts. All that stuff is regulated way past this. It's not a problem.
Yeah, but right, but Ripple is only one piece of it. What about that we're talking about over there?
Right, so both this has a common mode choke, and the thing plugging into it has a common mode choke.
Right.
Common mode choke, so that's on every piece of center.
Right, I see that, but the question is it?
It's a start. It's a start,
Well,
right?
what I'm saying is, I'm not trying to drive us. We need to cover that piece of it, just to make sure at some point when somebody actually goes to this, it's there. But maybe you're gonna know that there is provision at the IP side, there's provision at the rack.
Right.
But still, once you interconnect the whole thing, depending on what equipment or what storage device, which version you're using,
Sure.
those all go back. We have it.
That's why we have the compliance test when you get that project. It's making sure that if something says it's compliant, that it is, right? You should be able to induce all this stuff in there.
But
So
it's
still
a good
validated.
start. It's a good start. I just want to bring up that so we doesn't get left out.
I think one of the key things is when the folks deploy other equipment or IT gear in an area, they actually get the feedback from the community, like, hey, I have all this gear that's supposed to be in spec, but I'm actually seeing machinery from so I'm sure we'll have gaps at the point. Learn as we go. The important part is getting feedback back to the community, because that doesn't come back like
Yeah. Won't be able to cover that yet.
At least good on the open but once the integration going.
I mean, the integrator ultimately is going to make the product work. Power vendor, right here, power back, at the end of the day, just like if you're buying PC racks, the integrator is responsible for, balancing the loads on the breakers, the PDA, all those things. I don't know if they have the skills to do that.
That's what I'm saying. It's not putting the expertise on there.
Yeah.
So yeah,
Yeah,
you're doing now.
That's but
Most of the time, this one, I start with that going.
It'd be interesting to get some test plans. I don't know if it's this responsibility, but to work with compliance or with the integrators on like, hey, you're building an open rack for somebody, here's the kind of thing that you mentioned builder work doable. Right? And most integrators are probably just going to burn it in and call it good. They may not be testing, they move no things.
But in theory, right, that node, it's ready or whatever, it's already gone through the testing at P3, right?
Right.
Or,
The no design apps, yeah, but the integrated rack is, I think that's the.
right, yeah,
that's
you're
the
never
difference.
gonna get.
How do you, as an
Well,
integrator, how do I
so if it
validate
doesn't,
that?
right, then we need to go back and put that,
Totally.
you know, that's where your point of, for your integrator, knows something doesn't work, that's what we need to
Yeah.
figure out which meter that is. You know,
Yeah, until we
so
do
it
it.
has to be. Okay, thank you guys, I really appreciate the feedback, that's really what makes, I mean, the point, right, without this kind of feedback, right, we're not gonna be able to find those holes, or hopefully plug those holes before it shows up in the industry, so. Thank you very much for all your input, thank you very much. Thanks for coming out, and if any of you guys are gonna be showing up for Tuesday and Wednesday, or see you guys there.
What's on next Tuesday?
So for Tuesday, thank you for asking.
You gotta give them the hook, man.
You really good for that.
So we will have two manufacturers of open rack, kind of going through what their experiences have been developing open racks. So we've got Rital, and we're showing V2 rack, and we also have Schneider Electric. We've got a flat pack V2 rack. They're going to make available to the community, and I'm sure you'd like to know what's going on Wednesday as well. Thanks for asking. We are going to have, that's going to be focused on Fidelity Open Bridge racks. So we're going to have 3 different suppliers that are developing an open bridge rack. So there's Stack Velocity,
Cable, or sorry,
Belden.
and Jada,
Belden.
Belden and Delta.
Yep. All right. Thanks, guys. Appreciate it.